It is full wave bridge rectifier. Okay, so the main disadvantage with full wave rectifier is it is center tapped. Okay, the center point should be very much exactly we need to find. Okay, so that is what the drawback we have with the center tap full wave rectifier. So in order to avoid that, we are going with the full wave bridge rectifier. Okay, so the circuit for the same here, I will not use any center tapping to overcome the disadvantage whatever I have with respect to the center tap. That is what I'm trying to eliminate here. So here you need to remember the diagram. See, for others it was like so simple, but here we'll be using 4 diodes. That is what the drawback here. We'll be using 4 diodes. That is what the drawback. Okay. Here I'll have the resistance RL and I'll be using 4 diodes. Okay. So the directions of the diodes when you're drawing it is very, very important. Make sure that you draw your diodes properly. This is how the bridge rectifier is connected. Okay, so this is your bridge rectifier. So here there is no center tapping. Okay, so here we'll apply 230 volts 50 hertz signal. Okay, which is nothing but the sinusoidal signal. Okay, so this is a sinusoidal signal I am applying. Okay, so again we need to analyze what will happen for the positive half cycle and what will happen for the negative half cycle. Okay, so let us go with the analysis. First let me go with the, okay, fine. Along with this I will also take the input waveform, output waveforms. Okay, so this is my input waveform. This is my V input. The maximum voltage here is Vm. This is minus Vm. Okay, 0, pi, 2 pi, 3 pi, like that, so on. Okay, now I need to get the output voltage equation, waveform for the output voltage V0 and as well as IL, load current. Okay, fine. So let us go with the positive half cycle. So case 1, positive half cycle. Positive half cycle. Positive half cycle in the sense it is from 0 to pi. On from here to here you need to take. Okay, so 0 less than or equal to omega t less than or equal to pi. Okay, so let us draw the circuit for that. Redraw the circuit again for this. I'll exactly show you what happens to the diodes. Let me name the diodes. This is my D1, D2, D3, D4. Name the diodes also. If you just see the diagram, this one, this and this opposite ones are in the same direction. I'm just telling you how to remember as well. So if you just observe, this D1, D3 are in the same direction, D2 and D4 are in the same direction. Okay, so opposite ones are same and this is RL. Now I need to analyze for the positive half cycle. What happens during the positive half cycle? I need to analyze. So since I have positive half cycle, this terminal will be positive and this terminal will be negative. Now I need to check what happens to diode D1, what happens to diode D2, D3, D4. Okay, just check here. This is your P and this is your N. First I'm checking with the diode D1. P is connected to positive. Let me take the other color. See, from here it is connected to positive, P is connected to positive and N is connected to negative. Okay, so this diode D1 will be forward biased. P is connected to positive, N is connected to negative, the diode will be forward biased. Since the diode is forward biased, I can replace this diode with short. I can replace this diode with short. In the same way, check with D2. V2. This is your P and this is your N. Okay, P is connected to negative and N is connected to positive. The diode will be reverse biased. Reverse biased in the sense it will open. Okay, so it will open. Next, coming to D3 diode. So this is your P and this is your N. N is connected to positive and P is connected, N is connected to negative and P is connected to positive. So the diode will be forward biased. So here this diode will be forward biased in the sense it can be replaced with short. Next, to come back to D4. D4. This is your P and this is your N. N is connected to positive and P is connected to negative. So the diode will be reverse biased. Reverse biased in the sense we will open the diode. So this is what the this is how the waveform will. No, this is how the circuit will be for the positive half cycle. Anybody have any doubts with respect to the forward bias, reverse bias here? Please let me know. Is it clear to all of you? Is it clear to all of you? Okay, fine. So let me just, okay, ma. So let me just show the current direction. Okay, so always current will start flowing from the positive to negative. So this is where it starts. So it will start from in this, start in this direction. It will not go here. See, the current will start flowing in this direction. The current will start flowing in this direction. It will not go into this one. This open terminal, because since it is open, the current will not flow there, but it will start flowing in this direction. Again, it will not come here. The current will not come here, but again it will start flowing in this direction. Then again this way, finally here. Okay, so the current direction is in this direction. Okay, so like this the current is forming flowing. So there is a closed path, right? Only when there is a closed path, then only the current will flow, right? So is there the closed path available? Closed path is available or not?
Yes, ma'am.
Yeah, so since closed path is available, the current will flow in this direction, and if you observe, the current direction is in this way. So it means that this is positive and this is negative. This current voltage is nothing but V0, and this current let me name as IL. Okay, so IL current is flowing. Okay, so let us write the equation. This is, here it is, Vm sin omega t. 1 second, ma'am. Somebody is joined. Okay, so let me this voltage is Vm sin omega t. So now let us apply KVL to this loop. Okay, so move in the clockwise direction. Move in the clockwise direction. So the first one is minus Vm sin omega t. Minus Vm sin omega t. Current is flowing in this direction. So plus V0 or plus IL into RL. Plus IL into RL. Plus, okay, so I have I may have resistance, forward resistance with respect to diode D1. So RF1 RF1 into IL, RF1 into IL, plus I may have the resistance with the D3 diode. This was the D1 diode, this was D2 diode, this is D3 diode, and this is D4, right? So there may be some resistance available with the forward diode D3, so that RF3 IL, plus there may be some resistance of the transformer secondary, so RS into IL is equal to 0. So I have applied KVL. Anybody have doubts here? Please let me know. Anybody have doubts in this equation? Anybody have doubts in this equation?
No.
Okay, fine.
No.
So now let me take this minus Vm sin omega to t to the other side, and in between all this I'll take IL common. I'll take common, so it will be RL plus RF1 plus RF2 plus RS, which is equal to Vm sin omega t. Okay, I want equation for IL. IL is equal to Vm sin omega t divided by RL plus RF1 plus RF2 plus RS. Okay, so the year RF1 plus RF2 plus RS, this values will be in ohms only, like 10 ohms, 20 ohms, 5 ohms, like that. So which is very much less when compared with RL. So I can replace this entire thing with just RL. So IL is equal to Vm sin omega t divided by RL, or I can write as Vm by RL into sin omega t. let Vm by RL is equal to Vm by RL is equal to Im. So IL is equal to Vm, sorry, Im into sin omega t. This is for 0 less than or equal to omega t less than or equal to pi. Okay, so next I want V0. V0 is equal to IL into RL. IL is nothing but okay, let me just take this equation only. IL is nothing but Vm by RL into sin omega t into RL. This RL and this RL will get cancelled. Here V0 will be equal to Vm sin omega t. This is from 0 less than or equal to omega t less than or equal to pi. Okay, so this is how I've got for the positive half cycle. In the same way, you should also find for the okay, fine. Let me draw the diagram. So it is Vm sin omega t, and so whatever I will be applying, I'll have the same output at the load as well, and in the same way IL. Okay, here this maximum voltage is nothing but Vm, and here IL is nothing but Im sin omega t. So this is Im, maximum amplitude here is Im. Okay, and see the direction. You should be very particular with the direction. Direction is from right to left. Okay, the current direction for the positive half cycle is from right to left. We have to check the same thing in the for the negative half cycle as well. Okay, so now we'll go with the negative. Any doubts with the positive half cycle? Analysis of positive half cycle. Okay, so pi less than or equal to omega t less than or equal to 2 pi. Okay, so again here we need to analyze. Let me just take the diagram once again. Here I have diode D1. The opposite diodes are in the same direction. Okay. Okay, so this is diode D1, this is diode D2, this is diode D3, and this is diode D4. And here I am giving the negative half cycle. So negative half cycle, this will be negative and this will be positive. And here it will be Vm sin omega t itself. Okay, now again we need to analyze what happens to diode D1, D2, D3, D4. Can anybody tell me what will happen to diode D1, D2, D3, D4? Okay, first come with D1. D1 will be either forward biased or reverse biased. D1 will be either forward biased or reverse biased. This is your P and this forward. Is your yes. D1 is not forward biased. This is D1. P is connected to negative and N is connected to positive. So this will be reverse biased. P is connected to negative and N is connected to positive. It is reverse biased. Okay, since it is reverse biased, it will act as open. Okay, so here this D2 will be D1 will be open. Okay, so now come back to D2. Let me just erase. Next to D2, this is your P and this is your N. Somebody answered it is D1 was forward biased. No, I want to answer from the same person. How the D2 is biased? Forward biased or reverse biased? The same person, please answer me. Forward biased. CP is connected to positive, N is connected to negative. So this will be forward biased. Forward biased in the sense we'll replace with short. Okay, now come back to D3. D3, this is your P and this is your N. P is connected to positive and N is connected to negative. So P is connected to negative, N is connected to positive. So the diode will be reverse biased. So you will replace it with open. So let me just erase all this. Come back to D4. This is your P and this is your N. N is connected to negative and P is connected to positive. So the diode is forward biased. So forward biased diode you will replace with short. Okay, so this is so here if you observe, D1 and D3 are reverse biased and D2 and D4 are forward biased. here it's different, right? Here, where is that? Here, D1 and D3 are forward biased. D2 and D4 are reverse biased. Okay. So now again we need to check whether the current is flowing or not. If it is flowing, what is the direction of current? So here it is positive. So the current will start flowing in this direction. It will not go this side because it is open. So it will go in this direction only. Then again it will not go here. It will go in this direction only. It's going in this direction, right to left. Okay, again it will go in this way, and like finally it is flowing in this direction. Okay, so the dotted line indicates the current flow direction. Okay, so again you observe the current is flowing in this direction. So this side it is positive and this side it is negative. Okay, let this voltage be V0. V0. Let this voltage be V0. Okay, if you observe the direction of the current direction for the negative half cycle and the current direction for the positive half cycle, it is the same. So here also you observe it is from right to left. Okay, so the main motto why I'm again and again telling about this is, if the direction is same, like I'll get waveform to the upper side only. If the direction is negative, if I have opposite direction, instead of flowing in this right to left, if it is flowing left to right, then I'll get to the negative half cycle. For that only I was specifying that point very much. Okay, now again let us apply KVL. Okay, so let me apply KVL in the anti-clockwise direction only. So when I'm moving in the anti-clockwise direction, my first symbol is negative, minus Vm sin omega t. Next element is the diode, D2 diode. So plus Rf2 into IL. There may be a small forward resistance available with the diode D2. So Rf2 into IL current. Let the total current be IL only. Okay. So next plus IL into RL plus next this is diode D4. So it is Rf4 into IL. That's it, is equal to the transformer secondary may also have some resistance RS. So RS into IL is equal to 0. So again rearrange the terms, IL into RL plus RF2 plus RF4 plus RS is equal to Vm sin omega t, or IL is equal to Vm by RL plus RF2 plus RF4 plus RS into sin omega t. Okay, either you first take Im is equal to Vm by RL plus RF2 plus RF4 plus RS, where RF2 plus RF4 plus RS is very much less than RL. So your Im will be equal to Vm by RL. So we just substitute it. So IL is equal to Im sin omega t. Okay. Then V0 is nothing but IL into RL. This is for pi less than or equal to omega t less than or equal to 2 pi. Okay, so IL RL. IL is nothing but Im sin omega t into RL, or like Im is nothing but Vm by RL into sin omega t into RL. This RL and this RL will get cancelled. So your V0 is nothing but Vm sin omega t. Okay. So this is again for pi less than or equal to omega t less than or equal to 2 pi. So both the current directions are same. The for the negative from 0 to pi, whatever waveform you have got from 0 to pi, the same thing I'll get from pi to 2 pi also. Here also V0 also same. Whatever we'll get from 0 to pi, the same will be obtained from pi to 2 pi also. Again positive half cycle, I'll get again positive half cycle, get like this. Okay, so if you just summarize the entire result, the equations pertaining to your bridge rectifier is IL is equal to Im sin omega t for 0 less than or equal to pi less than or equal to omega t omega t less than or equal to pi. It is also equal to Im sin omega t from 2 pi less than or equal, sorry, from pi less than or equal to omega t less than or equal to 2 pi, or v naught is equal to Vm sin omega t 0 less than or equal to omega t less than or equal to pi. Vm sin omega t pi less than or equal to omega t less than or equal to 2 pi. So if you just see the waveforms, you can find that it is the same as your full center tap full wave rectifier. Center tap full wave rectifier. The output equations are same as your center tap full wave rectifier. So all of you make a note of whatever I'm saying now. See, it is still center tap full wave rectifier equations. Whatever equations I've got, this equations are same as your center tap full wave rectifier equations. That is the reason here we will not do any derivations. But in the exam, if they ask you to calculate IDC, VDC, VRMS, IRMS, efficiency, everything, no, you can directly use the same equations. It means that whatever derivations we have done for your full wave rectifier, center tap full wave rectifier, that are equally valid for your bridge rectifier as well. Okay, so same derivations except one. Okay, that is nothing but PIV. PIV based on the circuit we were calculating. So here we need to calculate the PIV. Except this, except PIV, all other derivations whatever we have done for center tap full wave, it is same for your bridge rectifier also. Okay, so in the exam, if they ask you explain bridge rectifier and show that the efficiency is so much, you need to derive the expressions how we have done for your full wave rectifier. Any doubts here? Anybody have any doubts here?
No.
Okay, so
No,
make this point very clear. Okay, so whatever derivations we have done for center tap full wave rectifier, all the derivations will be equally good for your bridge rectifier as well, except PIV. Okay, why I'm saying except PIV? Because PIV is calculated by using the circuit itself. Okay, so since the circuit is changed, the PIV may change. We will check whether the PIV is changing or not. Okay, so now let me okay, fine. Any doubts until here? Anybody have any doubts?
No,
Anybody want me to repeat anywhere? Please let me know. Okay, so I'll just go ahead with the PIV derivation. Okay, so PIV of bridge rectifier. Okay, PIV. When will I calculate PIV? I will be calculating the PIV when the diode is reverse biased. Okay, reverse bias. So take anything. This is what the diode. Okay, let me take when the diode D1 and D3 are forward biased. So that time you had like this. You had the circuit in this way. No, not in this way. You had the circuit in this way. D1 and D3 are forward biased. D1 and D3 are forward biased when it is when we are providing the positive half cycle. Okay, fine. The current see either D1, D3 are forward biased or D2, D3 are forward biased. Still there was current flow. So current flow was in this direction. If you just recall, so this is plus, this is minus, and this is V0. Okay. Now I need to calculate PIV here. Okay. So diode, how I've connected the diode, I've connected in this way. Okay, so generally if it is forward bias current flowing, then it will be plus minus like this here, but since the diode is reverse biased, the polarity will be opposite. Okay, so it will be minus here and it will be plus here, and here I need to find VPIV. Okay, VPIV. Okay, so in order to find VPIV, I will just take the equation in such a way that this part is covered. So what I'll do, I'll just apply KVL here. Okay, only in this loop. Can I apply in this loop? Anybody have doubts why I'm applying only here? Anybody have doubts here?
No.
Okay, fine. So let me just apply KVL here. So start from any point. So minus VPIV. Here it is 0. Then plus V0 is equal to 0. That's all. I have only 1, 2, 3 components. Okay, so VPIV, take VPIV to the other side. So it is nothing but V0. V0, you know that V0 is nothing but Vm. Why I am considering V0 is equal to Vm? Why not Vm sin omega t? Because Vm is a maximum voltage, right? This for the sinusoidal signal, if I represent it as A sin omega t, it means that the maximum amplitude is A. Okay, so in the same way, the maximum voltage that that will be there in the Vm sin omega t is plus Vm. That is the reason I have just written as Vm. Okay, anybody have doubts here? Please clarify yourself. Okay. Anybody have doubts here? So here I have got VPIV for your bridge rectifier as Vm, but for center tap we have got VPIV as 2Vm. Okay, that is what the difference. Okay, so this is less when compared to this one. Okay, so this is one more advantage of your bridge rectifier over center tap. Okay, so that's all with respect to the derivations and all. And here the only disadvantage what we have is it is using 4 diodes. Okay, so that is what the disadvantage here. Okay, so that's all with respect to the half wave rectifier, full wave rectifier, and full wave bridge rectifier. Okay, so whatever questions they ask you related to bridge rectifier, the derivations, the same derivations whatever we did for center tap, you can use the same derivations. Okay. Fine. Now that's all with respect to the rectifiers without filters. Whatever I have done with all these are without filters. Without filters in the sense, like filter in the sense like it will allow only certain frequencies to pass through it. Okay, so here whatever I have done, generally filters will be made by using RLC combination, LC combination, RC combination, like that. Okay, so here I have not used any capacitors or inductors. Okay, so this whatever we have done until now, all these are without filters. Okay, in the next classes we'll see with filters. Before going to the next topic, let us solve some of the problems related to this rectifiers. Is this clear to all of you until here? Anybody have any doubts? Until here, anybody have any doubts? Anybody in the class have got any doubts?
No, ma'am.
Okay. Okay. Fine. Now you note on the question. Go back to the first one. Okay. Note on the question. Where is that? It's not here. No. Next paper. Here I have a question. Note on the question. Second is 2B. I'm referring to 2B. Okay, so note on the question. A half wave rectifier, you can write in short as HWR. Okay, it's not wrong. A half wave rectifier from a supply, a half wave rectifier from a supply 230 volts 50 hertz. Okay, so half wave rectifier in the sense this is how the circuit will be. You will be using only one diode. Okay, and I'll have the load resistance RL. Okay, he's saying that the supply to this half wave rectifier is 230 volts 50 hertz with step down transformer step down transformer ratio 3:1. So here he has given the ratio between the number of turnings on the primary side and the secondary side. So can anybody tell me the equation relating the number of turns and the voltage? Anybody remembers that? Here he has given the ratio with the step down transformer ratio 3:1. In the sense he has given the number of turns primary and the number of turns secondary. He has given that as 3:1. Okay, 3:1 ratio. It is like the number is in this ratio. Okay, so now can you tell me what is the relationship between this number of turns and voltages in the transformer? Anybody can tell me? You have studied everything related to this, right? Yes, ma'am?
Yes.
So you don't remember?
V1 by V2 is equal to N2 by N1.
It is V1 by V2 is equal to N1 by N2. Okay, it is VP primary. Let me name it as primary secondary so that it will be easy. VP by VS is equal to NP by NS. This is what the relationship. Okay, so we'll use this, that relationship. Okay, fine. So with step down transformer ratio 3:1 to a resistive load of 10 kilo ohms. It means that he is saying that RL value is 10 kilo ohms. The diode forward resistance is 75 ohms. So I was talking about the diode forward resistance. It means that if the diode is forward biased, then the RF for that diode is 75 ohms. Okay, and transformer secondary is 10 ohms. RS, I was speaking about RS as well, right? So RS is 10 ohms. Okay. Calculate the DC current. DC current in the sense I need to calculate IDC. DC voltage VDC. Then efficiency I need to find. Then ripple factor. Okay, all this I need to find. Okay, so we will solve that. Have you all finished writing the question?
Yes, ma'am.
Okay, fine. So let me just go back to this. So first let us write the given parameters. So given, what is given? He has given NP by NS is equal to 3/1. Okay, and then he has given RL is equal to 10 kilo ohms. Then he has given VS primary of the VP primary of the transformer voltage is 230 volts. Then what else he has given? He has given RF he has given as 75 ohms, no? RF RF he has given 75 ohms only.
Yes, ma'am.
Then RS he has given as 10 ohms, right? 10 ohms. RS he has given us 10 ohms. Okay, now given all this, he is asking you to find what is IDC, what is VDC, what is efficiency, and what is gamma. All this I need to find. Okay, so in order to find this, so if I have to find IDC, well, how do you calculate IDC? You know, this is half wave rectifier, right? So for half wave rectifier, what is IDC equation? That's why I was telling you people, you have to remember the equations. IDC is IDC for half wave rectifier.
IM
by pi.
IM by root 2.
No. That is IRMS. IRMS is IM by 2. IM by 2. Okay. I need to find IDC. IDC is IM by pi. If I know IDC, I can find VDC. VDC is nothing but IDC into RL. Okay, this is how I can find. But first of all, if I want to find IM is nothing but VM by RL. Okay, Vm by RL. I need to know what is the Vm value, maximum peak voltage. I was mentioning, you know, here I have peak voltage as Vm. Okay, I need to know what is this peak voltage. Okay, so here one more thing, he has also specified RF and RS. So let me just take RF plus RS along with this RL. Okay, hope you are understanding. See, in the equations we were considering that RF plus RS is very less than RL, and I was neglecting these terms, right? So anyway, in the question he has given, so let us just take it. Okay, any doubts here?
No, ma'am.
Okay, fine. So we need to find Vm from the given data. So Vm, if I want to know Vm, let me just draw the diagram. If I want to know Vm here, Vm sin omega t. Okay, in this, if I want to know Vm, okay, I need to know what is the secondary voltage of the transformer. This is the primary voltage and this is the secondary voltage. What is that secondary voltage of the transformer? I need to know. So you have the relationship Vp by Vs is equal to Np by Ns, and he has given Vp value. He has given us 230 volts divided by Vs, which is equal to Np by Ns. He has given us 3 by 1. So from this I can find Vs is nothing but 230 by 3. So what is 230 by 3? See, I want you people to get your calculus. I'll just finish this problem and I'll leave you. It's already 11:40. Okay, so I'll just finish this problem and I'll leave you. So 230 by 3. Quickly. I want you people to answer. How much, ma?
69.0.
69.0. 230 by 3.
76.667.
76.66. 76.66. So whatever 667. Okay, fine. So whatever I'm getting Vs, it is nothing but the Vrms value. So Vrms value of the transformer secondary is given by 76.667. Okay, but I want to calculate Vm. Okay, so what is the old? How will you calculate? So this is a sinusoidal signal. Okay, so what is the Vrms value of this transformer? Sorry, this input. What is Vrms of this input? Okay, let me just come back again. So here I've got Vs. Vs is nothing but the secondary of the transformer. Okay, so this secondary voltage I've got. Okay, to this secondary voltage, whatever I will be having with respect to the transformer, that voltage is nothing but the RMS value. Okay, so RMS value. So from that RMS value, I need to find what is Vm. Okay, so what is the relationship we will have between Vrms and Vm for your sinusoidal signal? This is your sinusoidal signal. So what is the RMS value of this sinusoidal signal? Have you understood my question? Have you understood my question?
Yes. Repeat once again.
Okay, here this voltage is 230 volts, and then he has given some turns and all everything, and finally I've got Vs as 76.667, something like this I've got. Okay, so whatever voltage that is specified by the transformer secondary, it is nothing but the RMS value. This is my RMS value. So from this RMS value, I need to find what is the peak voltage. This Vm I need to find. Okay, in order to find this Vm, I need to know the relationship between RMS voltage and this peak voltage. So what is the relationship? That is what is my question. So if you observe, this is a sinusoidal signal. For the sinusoidal signal, how will you calculate the RMS value?
Vmax by root 2.
Very good. Vm by root 2. Okay, so it is Vm by root 2. So from this I will be able to calculate Vm. Vm is nothing but 76.667 into root 2. You quickly answer me. What is your Vm?
108.42.
108.42. Okay, so this is Vm. Okay, I know Vm. So from this Vm I can calculate Im. Im is nothing but Vm by RL plus RS plus RF. Vm is 108.42 divided by RL. RL value he has given us 10k. 10k in the sense 10,000 plus RS. RS is 10 ohms plus RF is 75. So just simplify 108.42 divided by 10085. What is the answer? IM.
0.01075. Point
0.10.
0.01075.
0.10. Come again, ma.
0.01075.
0.01075. Just check again. 108.42. Hey, once again, correct only, but okay, I am okay, fine. 0.010. Tell me, ma.
75.
75. Okay. 0.01075 amperes. Okay, this is your IM. I want IDC. IDC is nothing but how will you calculate IDC for half wave rectifier? It is IM by pi, right? Yes, IM by pi is for half wave rectifier. So it is 0.01075 divided by pi. Pi is 3.14. So tell me the answer.
3.42 into 10 power minus 3.
3.42 into 10 power minus 3. So I can write this as 3.42 milliamperes. This is your IDC. Okay, in the same way, I need to find VDC as well. VDC is nothing but IDC into RL. So IDC is 3.42 milliamperes, or you can write as into 10 power minus 3 into 10 power minus 3 into 10 in 10k. 10k is 10 into 10 power 3. Okay, so this will be equal to 34.2. 21. Okay, fine. 34.21 volts. Okay, this is your VDC. Okay, now I should also I got IDC, I got VDC from whatever he is asking. Where is it? I put the here. So IDC I've got VDC. Now I need to get efficiency, gamma. Okay, gamma, how will you calculate gamma? It is PDC by PAC. Okay, PDC is nothing but IDC square into RL divided by PAC. IRMS square into RL. This RL and this RL will get cancelled. I'll be left out with IDC square by IRMS square. But the thing is now I don't know what is IRMS. So I need to find IRMS. How will you find IRMS? IRMS is equal to IRMS of your current is IM by 2, right? IM by 2 is the IRMS value, right? Anybody is getting confused with root 2 to why I'm taking 2 root 2? Any confusion there?
No.
Okay, fine. So IM is 0.01075 divided by 2. So what is the answer?
5.37 into 10 power minus 3.
5.37 into 10 power minus 3, which is nothing but 5.37 milliamperes. This is IRMS. Okay, fine. Let me just take the efficiency. Efficiency is, I got the equation as IDC square by IRMS square. So IDC, what was my IDC value? I've got 3.42 milli. 3.42 milli in the sense 10 power minus 3 whole square divided by IRMS. IRMS is 5.37 into 10 power minus 3 whole square. Anyway, this and this will get cancelled. So I'll be left out with 3.42 whole square divided by 5.37 whole square. What is the answer?
0.405.
405. Okay, so if it is in percentage, eta efficiency will be nothing but 40.5%. Okay, so if you just compare your ideal values, it will almost same. Okay, whatever ideal values we have got for half wave rectifier and full wave rectifier, no, it will be almost the same. Okay, in the same way, now let us calculate gamma also. Gamma, it is root IRMS by IDC whole square minus 1. Okay, so just substitute the values. So under root of IRMS value we have got as 5.37. 5.37 into 10 power minus 3 divided by IDC. IDC is 3.42 milli. 3.42 into 10 power minus 3 whole square minus 1. Okay, so anyway, this and this will get cancelled, so we will be left out with just simplify this and tell me. Hope you all know how to use the calculus, right? Yes.
Yes, ma'am.
Okay. So gamma will get as
1.1.
1.21, right? So if you just check these values, whatever efficiency and ripple factor will be getting almost the same. Okay, so that's all for now.